Hi guys, welcome to Science Chomp. Today we're going to be looking at interference. Interference is when two or more coherent waves combine to form a resultant wave of a greater or lower amplitude. There seems to be quite a lot to unpack here, so first of all let's figure out what coherent waves are. And there's two requirements to have a coherent wave. First of all, the waves in question, and there's always more than one wave. You can't have one single wave that's coherent with itself. It has to be coherent with another wave. So the two waves have to be in constant phase difference and they have to have the same frequency. When it says same frequency, that also means it's going to be the same color, because if you start changing the frequency of light, you end up with different colors. For example, blue light has a much higher frequency than red light. So just bear that in mind. So it needs to be monochromatic. So what do we mean by phase difference? Well, here we've got a couple of waves. Hopefully you can see it. These clearly have the same frequency, but there's a slight phase difference. It's not perfectly aligned. However, that phase difference is constant all the way through. So that's a constant distance apart that the waves are, and as a result you can form an interference pattern. These waves are perfectly in line, so these are perfectly lined up, and as you can see they're the same frequency, same wavelength, everything like that. These waves are not coherent, so as you can see the frequency is different on all of these different waves here, and they're not all in phase either. These ones are coherent, so you've got the same frequency and they're in the same phase as well. Now what happens is when you have these coherent waves, when they interfere with one another, they form this interference pattern that you can see. Now this interference pattern has maxima, the bright parts, and minima, the dark parts. These are also called interference fringes, so you can say they're bright fringes and dark fringes. So in the center we've got this really bright maxima, and then all of the rest of the bands are separated by minima, which are the dark bands. The central part, we call it order 0, or m equals 0, and then going outwards you have 1 on each side, so m equals 1 is the next bright patch, m equals 2 would be the next bright patch, and again it will be on either side. Now why does this happen? Well, it's all down to this thing called superposition. Superposition is simply placing something on top of another thing. So you've got two waves here. As you can see, they're the same frequency and they are perfectly in phase. When you put them on top of one another, what happens is this plus this ends up giving it a really big wave, and you end up like this. This is called constructive interference. On the other side of it, we have this this blue wave, and as you can see, this frequency is the same, but they are out of phase. And as a result, when you combine the highest amplitude with the lowest amplitude, you get an amplitude of 0. So when you add this and put it on top of that, you end up with a line like this. Incidentally, this is how noise-cancelling headphones work, but just with sound waves. It's quite interesting, it completely eliminates it. So you have constructive interference at the top and destructive interference at the bottom. And this is what causes the interference patterns. Now this was discovered by a young man called Young. So he had this experiment called a Young's double slit experiment. And what the two slits effectively provide are two sources of light which are perfectly coherent, because at the end of the day it's all coming from the same source and you've got two slits. And where the waves overlap, you end up with interference patterns, as you can see in this diagram. Now, this also gives rise to an equation. So this is our interference equation. We've got the wavelength lambda is dx divided by L. So d is the distance between the centers of the slits, x is the distance between the successive bright fringes, and L is the screen distance from the slit. they're all measured in meters, by the way. So meters here, meters here, meters here, and meters here. And one thing that you have to bear in mind is they're going to mix up the units. They're going to put centimeters with millimeters and nanometers and all of that kind of stuff. So what you've got to do, if something's in centimeters, just put times 10 to the minus 2 meters. If it's in millimeters, it's times 10 to the minus 3. If it's in nanometers, it's times 10 to the minus 9. So just bear that in mind when you're doing these calculations. You need to understand this. The other thing which you need to know is how to rearrange the equation, and often what they're going to ask you is the distance between the successive bright fringes, because at the end of the day, this experimentally is what you'll be measuring. So if you put that over there and this down here, you end up with x is equal to lambda L divided by D. Which means if you make this bigger, this should become smaller. If you make the wavelength or the screen distance bigger, then x, the distance between the successive bright fringes, should become bigger. Okay, so let's just test this on the simulation. Okay, so here we have the Java Lab Young's double slit experiment. And you can do all sorts of things with this. So for example, you can change the distance between the original slit and these slits. And actually, if you do that, it doesn't change the pattern of the interference. And as a result, you're not going to find it as a variable on your in your equation. Okay, you can do various things. You can change the color, and changing the color is changing the wavelength, or you can even say changing the frequency. So there's that. That's one thing. You can change the distance between the slits like so. And you can see how it changes all of that. What else can you change? Well, that's about it. Let's just stick with those for now. So remember, with this experiment, we've got x, which is the distance between these fringes over here, is wavelength times the screen distance divided by the distance between the two slits, which is that distance that you can see by the cursor. Now, what happens when we make the distance between the slits bigger? Well, let's have a look. So have a look. This is the distance between the fringes on the side here. We make this d bigger. Make d bigger, x becomes smaller. Okay, that seems to make sense according to the equation. Let's put it back to around here. It's kind of a neutral level. And what's interesting is you can see the constructive interference is represented by the dots here, and the destructive interference is basically in between all of that stuff. So that's quite interesting little quirk of this simulation. Okay, what's going to happen if we change the wavelength? If we make the wavelength bigger, so you're going to go from 530. Oh, bigger wavelength is this way. Now have a look. We went from 530 to 700. In fact, let's go all the way here. This is the smallest. That's the biggest. So the bigger the wavelength, the bigger the distance between the bright fringes. So the bigger x becomes. Let's now look at the screen distance. Now the way we affect the screen distance is like this. So small screen distance, that's the smallest it's going to get. And then big screen distance. Again, let's just move this all the way over there. And the screen distance, by the way, is between the double slit and the screen. It's not the first one. So let's move this from here all the way backwards. And as you can see, the bigger the screen distance becomes, the bigger the distance between the fringes becomes. So there we are. I'll leave a link to that simulation in the description. It's very useful for understanding this. Now there is one last equation that we need to deal with. It's just a modification of this. As you saw, there's several fringes that we're dealing with, And the one in the middle, we say that's the order 0, so m equals 0. So basically it's like this. You got this situation. Excuse the accuracy of the drawing, but this is going to be m equals 0. This is m equals 1. This is m equals 2. That one will be m equals 3 along with that one. Okay, so this is the order of the maxima. So the central one is m equals 0. Now, when we're dealing with that, we say m lambda equals xmd over L. Now, it's very important to take into account that you're multiplying the wavelength here, but this distance is xm. It's like, for example, it would be like from here all the way to here. You're not going to say, so this would be for m equals 2. You don't do double the distance. It's not like the distance times 2. You just measure that distance, okay? But I'll go over the calculations in part 2. And that's it for interference, the theory of it anyway. Thank you very much for watching, and I'll see you in part 2.